Hello. Am I audible?
Yes, sir, audible.
Okay, thank you. We'll start it. So, uh, welcome to the week 5 live session on the course NOC25 EE-39. The course is titled Fundamentals of Semiconductor Devices and it's taught by Professor Digvijaya. I'll be the TA for this session. So, the schedule as usual for these sessions is every Sunday 3 p.m. to 5 p.m. So, let's quickly go through the guidelines. In case you have any query, you can raise your hand or you can ask it in the chat window. Please make sure your microphones are muted when you don't intend to speak. And uh, let's try to make this an interactive session. And for that, I would appreciate your cooperation. I hope you would have kept pen and paper handy along with a calculator for calculations. And uh, session recording link and the lecture notes, they will be shared by the NPTEL course team in the due course of the time. So the prerequisites for this session include the last week's lectures, which covered following topics. Uh, you learned about the applications of the PN junctions, the breakdown of the junction and CV profiling, and then you were introduced to Schottky junctions under equilibrium, and Schottky junctions under bias. Okay, so we'll directly start with first problem today, right? So in a certain Schottky contact, a negative bias is applied on the metal with respect to the n-type semiconductor. Compared to the equilibrium, the magnitude of the peak electric field and the width of the depletion region. I mean, what does, how does your biased peak electric field compare with the equilibrium peak electric field, and how does your depletion width under this particular bias configuration compare with the equilibrium one? That is the question. So start. Firstly, let's draw equilibrium band diagram. For this, right, we have metal semiconductor junction, right? And the semiconductor is N-type. So this would be metal, right? This is your vacuum level E0. And this be your Fermi level, right? The metal side.
Sir, B option, sir.
B, uh, that is incorrect. We'll see why. So this is your E0, right? And this is your metal Fermi level. And uh, what about the semiconductor side? In semiconductor, you'll have, I mean, I'm drawing when they are not in contact, right? Then we'll draw the equilibrium band diagram when the contact is established, right? So this is your semiconductor. This is your E0. This is your EC pin. This is your EF. This is your EV, right? So under equilibrium, when your metal and semiconductor are, I mean, brought into contact with each other, your Fermi level would be constant throughout, right? So this would be your Fermi level. This is your equilibrium case, right? So this is EF, right? And accordingly, we'll draw the This was your uh, E naught, right? For your Palladium, here that phi m is greater than phi s, right? This is your phi m, this is your phi s, right? Which is reasonable actually. So, okay, this is E naught, and now um, this is a junction. Since phi m is greater than phi s, so E naught on semiconductor side would start at a lower level, right? So this would tilt like this. Right? This is E naught. And likewise, your EC would track it. Similarly for EV. Right? This is your here. So now this is EG, right? Which is this, right? What about Q chi? That also is constant, right? And that is equal to this on infinity, right? Q chi. And then we have this is the quantity of interest. Right? We need to find this here, Q phi b, right? And I mean, from the band diagram, your Q phi b would be equal to your Q phi m minus this Q chi, right? That is your Q phi b. And in the question, we have been asked to comment upon the magnitude of the electric field, right? So this is how your uh, E varies, right? The E varies this. This is the junction. This is how E varies, right? And uh, how would potential vary? Potential would vary like this, right? If this is E, so this would be this is your phi, right? And then you have electric field. This is how that is. So what is the relation that relates your potential to the electric field? Your E is equal to minus d phi by dx, right? So uh, if we take the derivative of this and uh, multiply that by the negative sign, so uh, this v is equal to 0. Now we are interested in electric field profile. Right, this was phi, this was a, so this is no, and this is over x, right? Now So from this relation, this would be my electric field, right? Very somewhat right. Right, this would be the peak electric field, right? And that would occur at x equal to 0. How I arrived at this is by using this relation, right? I had phi, which I obtained from this, right? Uh, no, your E is equals to minus q times phi, right? I used this to get phi from this band, right? And then once I have this electric field profile, this would be the case corresponding to the equilibrium, right? Now let's see how the band diagram, or I should say the electric field profile changes when this bias configuration is used, right? So if you apply negative bias to the metal with respect to the n-type semiconductor, that is as if you apply a positive bias, right, uh, at the n-type semiconductor. So let's do that. If you do that, we copy this. Oh, now, I just mentioned that if you, in the question it was given that for this Schottky contact, we are applying negative bias at the metal with respect to the n-type semiconductor. So that is as if you apply positive bias at the n-type semiconductor. And what happens uh, to the bands when you apply a positive potential? Should I move them upwards or should I move them downwards? I'll move them downwards, right? So this would be your say new E naught. Likewise, your EC would also change. Your EF will have EFS in the semiconductor, right? Uh, Once you apply this positive potential. Likewise, you'll have EV, right? So this is the notation. This is, I would say, flying reverse bias, right? Because positive potential to the n-type semiconductor, I mean, I can write that as a reverse bias. And, uh, this is your equilibrium, right? And this distance would be VR. right? How much your EFS differs from this EF level, that is V dash tells. So what would happen to these profiles now, right? Because we have to comment uh, the relative magnitudes of the peak electric field for these cases. We use red, right? So your band profile, the new band profile was come down, right? So uh, and uh, likewise you'll have, okay, so this slope would be more, right, at the junction. So that's why I'm showing, I mean, on the magnitude scale here, I mean, E decreases. In other words, I mean, E increases in negative sense, right? Your magnitude of peak electric field increases at the junction. This is your electric field. So that's why I said, okay. So one of you answered it as B, right? So first part is right in the sense that your peak electric field magnitude increases compared to the equilibrium case. But the second part is what happens to the width of the depletion region. So I assume you know if you apply a reverse bias, what happens to the depletion width? Can anyone unmute and let me know?
Increase, sir.
It increases, right? So that's why option D should be correct, right? Not B. Your depletion width won't decrease for the bias configuration that we have been provided in the question. So let me then just write it. Your peak electric field, sorry, magnitude, right? Increases. Likewise here, depletion width increases. Reason, this is reverse bias, right? So is this question clear? Should I repeat anything? May I write in the chat or just unmute and let me know? Yeah, you're fine with this question and should we move ahead? Okay, no questions. I'll move ahead. Your next question is chromium N-type silicon metal semiconductor junction, right? And in this, your semiconductor is doped with Nd equal pretend the per 17% unit Q. You need to calculate the Schottky barrier height and the built-in potential at T equal to 300 Kelvin, right? Uh, let's first make this equilibrium band diagram for this case. Again, uh, this is metal N semiconductor junction, right? So this would, I mean, the band diagrammatic equilibrium would look something like this. Right, it's provided that the work function of this chromium metal is 4.5 electron volt. That is the reason I wrote 4.5 electron volt on this side, and affinity is 4.05, right? Silicon affinity is 0.4.05 electron volt. So if I would draw that, that would be something like this. This is EC. Then you have EF. And EV. This is EG, right? This is electron affinity. So this much would be 4.05 electron volt, right? And uh, we are interested in computing the barrier height. We are interested in this quantity. This is Q5. This is Q5. So how much would this Q5 be equal to? This affinity is constant throughout the semiconductor, right? It's equal to 4.05 electron volt far away from the junction, and it's also equal to 4.05 at the junction, right? Because this is a material property. That won't change even if equilibrium is established, right? So how much is Q5B if this is 4.05? I mean, this should be clear from the figure, right? Please answer it. How much should be Q5B? Was I clear? Should I repeat? 0.45 electron volt. Okay, so one of the students has answered it as 0.45 electron volt, right? That is correct answer because your Schottky barrier height Q5B would be this minus this, right? That is the difference of these two. Your metal work function, which is 4 minus 4.5 electron volt, and you need to take the difference of that with your affinity value, right, of the semiconductor silicon, right, 4.05 electron volt, which is equal to, that is equal to 0.45 electron. So your, uh, I mean, although that's not needed, 5B is 0.545 volts, or Q5B, the barrier height is 0.45 electron volts. So now what about the built-in potential? What about this? So far we computed this, right? Schottky barrier height. This is your Schottky barrier height. Now what about your built-in potential by BI? What is built-in potential by definition? Your built-in potential by definition, your Q, what should I say? Q, sorry, phi BI. Phi BI is equal to your EC, or take any one among them, EC, EV, or EI. EC at the junction minus EC in the bulk, right? That's how you compute it. And from uh, this diagram, this much would be your phi BI, right? And this is equal to this whole total minus this Q phi, right? Because your Q phi F is the difference between EC and EF in the metal side. Sorry, in the semiconductor side. I assume you know these things. So your phi BI would be equal to, right, write it. I mean, if I write this as Q phi BI, would be equal to your Q phi B minus Q phi F, right? And how would you compute this Q phi F? Your Q phi F would be equal to KT ln of your uh, KT ln of this NC by NA, right? Yeah, and I'm using this one. If you use this formula, right, N is equals to NC exponential of minus EC minus EF by KT. From this one, you'll compute this to be ND, right? Assuming 100% ionization. I'm replacing your N by ND. So now if you plug in the values, you'll obtain this Q phi F to be equal to, would be 0.026 multiplied by ln of 282, which is approximately 0.15 electron. Okay, and okay, so this was your Q phi BI, right? So this we already computed, right? This is the Schottky barrier height. So if we subtract this from the Schottky barrier height, we will obtain the building potential. Right? So your uh, Q5I, which is equal to this thing, your Q5P is 0.45 electron. Subtract Q5F from that, right? Which is 0.15, which is 0.3 electron. And your 5BI would be 0.3. Okay, that finishes this question. What is ND here? Okay, ND is this, right? ND is uh, doping concentration of the donors. It was provided, right? Any other question or query regarding this problem? No? If not, we'll move on to the next one, right? The next problem is as follows, right? You need to consider a metal semiconductor junction that was given in the previous question. And instead of N-type doping, you now consider it to be as a P-type dope, right? P-type dope silicon, with the dopant concentration Na equal to 10 to the power 17 per centimeter cube. What will be the Schottky barrier height and building potential in this case? This I'll leave as a homework. Okay. And all of you can try this out, and if you face any difficulties, you can let me know. Right?
Kindly reply, sir. Sir,
Sorry,
repeat, sir. Kindly repeat, sir.
which one? Previous problem?
This problem, sir. Regarding this problem,
Oh, okay. I mean, I was
question number
saying,
5.
should I assign this as an homework, or do you want me to work it out here, the live session? I mean, I was thinking of assigning it as homework. Okay, I'll do it in this session.
Do some hints, sir.
Sorry, I'm not able
Sir,
to hear your
hints, sir.
voice.
Do some hints, sir.
I'll work it out. I'll show this problem in this session. Hope that answers your query. So this is your metal semiconductor junction, and your semiconductor is P-type, right? So and if it's P-type, then your this Fermi level would be near the valence band, right? So now, if you make the equilibrium band diagram, it would look something like this, right? So now you need to align first the Fermi level, right? And while aligning that, you'll move it a little upward, right? So all the bands will move upward. This is EF. This is E0. This is EC. This is EV. This is your junction. Okay. Now, uh, now you need to compute first the Schottky barrier height. What will be the Schottky barrier height for this question? The Schottky barrier height would be this. And this would be the Q5B. Right. And uh, what about this Q5BI? The built-in potential. The built-in potential would be this much, right? Here EV0 minus EV bulk. Okay. In the previous problem, we defined it to be EC0 minus EC bulk, right? But EC and EV track each other, right? So we can likewise say EV0 minus EV bulk. So compute uh, these two and let me know the answer. How much is this? This is your 4.5 electron volt, right? This is unchanged from the previous problem. So your work function will be same. And your affinity, how much would your affinity be? Would be 4.0 for electron, right? And yeah, and this much is EG. This much is Q5, right? So how will you compute this? Schottky barrier height. Schottky barrier height is equal to this height minus this, right? This much you know. This is your metal work function, 4.5 electron volt. But what about this? This is sum of two things, right? What are those two quantities? Their affinity and band gap, right? Material properties, they won't change, right? They would remain same throughout the semiconductor, right? So this much is affinity, this much is your band gap. I mean, I have not drawn this to the scale, but you get the idea, right? So take the sum of these two, subtract this from the sum, you'll get Q5. Okay, I'll just write the answer. I discussed how you will compute it. So your Q5 would be equal to 0.67 electron volt. Now, what about Q5BI? This is simply the difference of your Q5B and this, right? This is equal to Q5B minus Q5F. Done. And if you'll compute it after evaluating 5 and substitute it right back here, you'll get Q5BI as 0.535 electron volt. So your built-in potential 5BI is 0.535 volts. Is this fine now? All you need to do is work this out. Right. Let me write the formula as well. Your Q5F will be equal to KT ln of your NV by P. Right. I mean, here it was NC by N. I used N equal to ND in this question, right? And here I'll use NA for this, right? Right, equals NA. And what is NA equal to? This question, NA is 10 to the power 17 per centimeter cube. Use that and you'll get 5. Value of Q5 you'll obtain is 0.135 electron volt. Right? I'll move ahead. What about the next problem then? Is this clear? Please answer yes, no. Does anyone have any question or query regarding this problem?
The answer would be Q5BI equal to 0.535 volt.
That is what I wrote. Yes, correct answer. Your Q5BI is 0.535 electron volt. Thanks for trying that out yourself as well. So we'll move on to the next question then, right? So the next question is, okay, I'll leave this as an homework, right? This is nothing but, I mean, substitution. I'll provide you the formula and then you'll use it. So here you have been asked depletion layer width and electric field at the interface, right? Uh, and the junction is metal N-type junction, metal N-type semiconductor junction. Your xt would be equal to your square root of 2 epsilon s phi bi plus vr whole divided by q nd. What is this? This is built-in potential. You'll compute this built-in potential. Actually, we have already done that, right? This is the same junction that was given in question 4. So in question 4, the built-in potential that we obtained was 0.3 volt. You'll plug this 0.3 volt into this expression and you'll obtain this xt, right? And the value of nd, what is the value of nd that you'll use? Same, this one. All the quantities have been taken from question 4. This is an extension of question 4 in that sense. So you can obtain this. I'll provide you the answer. You can verify on your own. So the answer is 26 micrometer. Okay. So that is the depletion layer width in micrometers. What about the electric field? The E max. Once you obtain this depletion width, your E max is simply QND by epsilon times this xt, right? Do you agree with this? See, the reason is this is xt, right? I'm interested in finding this Emax. All I need is slope, right? What is the slope of this? If I multiply slope with this, I'll get this, right? And slope is nothing but this quantity, UND by epsilon. I mean, you would have already seen these expressions. I was just mentioning them here again for your reference. So Emax value that you will obtain is 3.95 into 10 to the power 5 volt per centimeter. So your correct answer is option A, right? Please work it out. I mean, do the maths. That would be, I mean, that would come handy in exams, right? That would also serve for you as a practice. So now, again, consider the same junction that was given in question 4. Now the junction is subjected to 5-volt reverse bias. You need to calculate the potential drop across the semiconductor in volts and the junction capacitance per unit area. See your effective band bending when it's subjected to uh, reverse bias of 5 volts would be your built-in potential plus this reverse bias, right? 5bi plus vi. And 5bi in this case was this one. If you add 5 to this, that would be the potential drop. So the potential drop would be 5.3. What about the junction capacitance per unit area? The junction capacitance per unit area, you can obtain that from Cg, that is equal to epsilon s by xt, right? Xt we already computed here, right? Use that in this and you get P2, right? So your Cj, if you compute, comes about as 4.5 nanofarad per centimeter square. You'll work it out yourself, right? Because this was known, right? So since the junction capacitance per unit area asked was in nanofarad per centimeter square, and I got this, so that's why this option is correct. Option C. Next one is this, right? Uh, the capacitance C of a Schottky diode is given by the relation 1 by C square is equal to A minus BV, where V is the applied voltage and B are the constant coefficients. You need to calculate the built-in potential phi Vi and the donor concentration Nd. You can assume permittivity of the semiconductor to be equal to epsilon s, the junction cross-section area to be equal to A. Given these two, I mean, assuming these two, you need to find the built-in potential phi Vi and the donor concentration Nd. this is the capacitance, right? So this would be my junction capacitance per unit area times A, right? So your C would be equal to epsilon s by xt times A, right? And what is xt? The expression of xt you already know. This is xt, right? So I'll write C is equal to epsilon s whole divided by square root of 2 epsilon s by q and d by bi means v this times this area. So this gives us that here C is equal to square root of q epsilon s nd whole divided by 2 pi vi minus v times area of this. So this implies your 1 by c square. If I take the reciprocal and square both sides, it will be 1 by c square is equals to 1 by a square times 2 pi vi minus v whole divided by q epsilon s times nd, which is your 1. Sorry. So your 1 by c square is equal to 1 by a square. Uh, 2 pi bi a square q epsilon s nd minus 2 whole divided by a square q epsilon s nd times v, right? So, I mean, I can comparing with this equation. What are my a and b? My a is this, and my b is this. So, which option is correct? Option B, right? Option B is the correct answer. Now, which of the following is not correct regarding the metal semiconductor junction? Okay, skip this question, right? I'll leave this as a homework problem for you all. Is that fine? You can try it out, or I can do one thing. I'll discuss this problem very briefly and then uh, leave this problem for you to solve from there onwards, right? So first, what is asked in this question is, what is the electric field in the semiconductor at a distance of 1 micrometer from the junction? So in other words, you are being asked to find a general expression of E of x, and that if you'll substitute one distance of 1 micrometer from the junction, you will obtain this uh, the value of the electric field in the semiconductor at that point, right? So your E of x is q nd whole divided by epsilon s times your x minus xt. What is XD? XD is XD is uh, Q epsilon is pi bi plus VR. Right. I mean, minus V in general. Right? So depending upon where V is the potential, right? And if you apply a reverse bias, that would be a negative number. So this would be phi a plus VR likewise. So in this problem, where metal contact is kept 5 volt below the semiconductor, right? And the semiconductor is N-type doped, right? So we are applying a positive potential of 5 volts on an N-type semiconductor, right? That is your, this would be reverse bias, right? So your V would be minus 5 volt. And then you can proceed and calculate first XD, and then you can substitute that XD here, and you'll obtain electric field profile, right? And then you'll use, should I say, once you obtain this E of X, then you'll find E of 1 micrometer, right? Because here X is the distance from the junction. At X equal to 0, that is your junction, actual junction, right? And as you increase X, you go away from the junction. So you will uh, solve this from here onwards and see if you'll obtain this. Your E of 1 micrometer would be equal to, that would be equal to, Q ND by epsilon s 1 minus your XT comes about as 2.74 micrometers. I'll take this micrometer common, convert it to volt per centimeter. So this would be 10 minus 4. This is expression. Substitute ND epsilon S Q into this expression and obtain E. Okay, so that finishes this question. Now the 10th one, right? Which of the following is not correct regarding a metal semiconductor junction? You have to identify an incorrect statement, right? Let's look at this statement one. The thermionic emission depends on the shape of the band bending inside the semiconductor near the junction. Just a second.
The question A, sir. Answer A.
Uh, am I audible?
Yes, sir.
Okay, okay. So yeah, as you answered it, the correct answer is option A. Sorry, my buds were discharged. So your thermionic emission does not depend upon the shape of the band bending inside the semiconductor junction. And the other three statements are correct. Returning current through a triangular barrier at the junction, it increases with the doping concentration in the semiconductor. But diffusion transport through a junction is negligible in case of a reverse pass, and your thermionic emission transport enhances with the increase in temperature, right? And then you have uh, these two problems, right? Uh, we already computed expression for this, right? Uh, your 1 by Cj square was equal to your 2 phi bi by a square epsilon s q and d plus 2 by epsilon s a square q and d. I'll copy that, right? It already. See, this is VR, right? So that, I mean, if you'll express it in terms of VR, then this is the right way, right? This sign would be plus then, because V is equal to minus VR. That's it. So now your intercept would be this much. Your slope is this, right? And what have you been asked? What is the value of the donor concentration, right? The quantity that you have been provided is this one, right? And what is this? This is the intercept on the x-axis, which you'll obtain if you put y as 0, right? If you put this as 0, uh, if you'll put this as 0, then this is 0 is equals to 2 phi bi by a square q epsilon s nt plus, okay, so this is 2 whole divided by a square q epsilon s nt pr, right? And we need to find nd. Right? We'll do it in alternative fashion. What about this distance? Let this be x, right? If this is x, then your x by is 0.75 or 725, sorry, would be equal to your slope, right? And your slope is this. So your m is equal to, sorry, your, your slope value, right? Which is 2 by a square q epsilon is nd, that is equal to x whole divided by 0.725. Can you now determine nd? You are also provided this, right? The value of the slope. So you can use, I mean, your m is 6.15 into 10 to the power 15 farad per centimeter square, whatever the units, right? So you can use this m to find what's x. You can substitute x here. That will give you nd because nd is the only unknown. Right? If you would do that, your uh, and using the fact that your Na is much greater than nd, right? Since it's one-sided silicon p-n junction. So that means your uh, okay, then you can use this in XD, right? And evaluate XD. This wait, your CJ was epsilon s by your CJ was epsilon s by XD times A, right? What is XD? Your XD is square root of 2 epsilon s phi bi plus VR divided by Q 1 by Na plus 1 by Nd. Here Na is much greater than Nd, so you can neglect 1 by Na, right? So you'll only be left with 1 by Nd. You'll only have Nd here, right? And then you can proceed and obtain an expression of 1 by Cj square, right? Which will be of the form of y is equal to mx plus c. Equate the slope with this, use this value, I mean, using this, and then you'll obtain Nd. I'll write the answer, right? Your Nd is 1.96 into 10 to the power 15 per centimeter cube. Try this out and you can mail me if you have any doubt or so regarding this question. Is this fine? And in question one, what is the concentration of acceptor atoms? You can also find out that as well. So problem one and two would be your homework problems. You'll work them out and you can let me know via mail if you have any query regarding that, and I'll reply by providing solution or answering that query. Does anyone have any questions? No? If not, we'll be ending the session here, right? Thank you. I'll be ending the meeting.
Thank you, sir.
Thank you.